Let's talk a bit about ExoMars. First of all, he has gone through a number of iterations. First it was a European-only mission. Then at a certain point, around 12, we were going to do it together with NASA. Then NASA pulled out and we went with Roscosmos. And now, in its final configuration, I hope it will be the final configuration, it's a cooperation between ESA and Roscosmos with some important NASA contributions. And it's got 2 missions, so you can think of it as a mini program. So I'll talk about both of them, but I'll concentrate more on the second one. So the first mission was launched in October 2016, and it consisted of 2 elements. First of all, the largest spacecraft ever launched to Mars by more than 1,000 kilos. A large orbiter with 4 instruments, we'll discuss them in a second, that has 2 functions. One is to do science, and the second one is to act as a data relay platform for all future landed missions. Because at the moment we're using the Mars Reconnaissance Orbiter from NASA, but that is getting a bit old. And so the idea was that then TGO, the Trace Gas Orbiter, will supplement MRO, and if MRO were to fail, will take over. So we are hopeful that both satellites will continue to operate for a long time, and in that way we will have a mini network for communications. The reason for this is that rovers and landers cannot talk directly to Earth with a large enough data rate. You would have to have antennas that are too big. Instead, we put a little antenna on the rover and a big antenna on the orbiter, like you see here. The other element of the 2016 ExoMars mission was Schiaparelli, a 600 kilo capsule whose objective was to learn how to land on Mars for ESA, because we have never done it before. We still haven't done it. So this thing worked, sort of. It worked fairly well until the last 45 seconds before landing, at which point something went bad in the calculation of the altitude. The computer took the wrong decision and we crashed. The good thing about Schiaparelli, nevertheless, is that for the first time, because this is not done in the NASA missions, we implemented a transmit while you descend strategy. So everything that was being calculated by the computer, all the information from the sensors, it was all being transmitted to the Trace Gas Orbiter during the entry, descent and landing. And that's why we were able to tell exactly what had gone wrong during the landing. So, the main objective for science on the Trace Gas Orbiter is to study trace gases. These are gases that exist in tiny amounts in a Martian atmosphere, let's say at less than parts per million level. And chief among these is methane. Why? Because on methane we have potentially an important biosignature. On Earth, a large fraction of the methane produced in our planet is the result of the activity of living microbes. People think of the guts of cows, but for the most part they come from the swampy areas of the planet. There are other ways to produce methane that have to do more with either past life, in the case of, for example, the release of gas from extinct microbial material, but we can also release methane from the thermal maturation of kerogen, for example, and as we discussed during the first presentation, it is possible also to produce methane by hydrothermal means. What I told you about the reactions of hot water with mafic minerals, that process one of them is called serpentinization, for example. That goes from the peridotitic components of the mantle to serpentinite, and in the process liberates hydrogen, which in the case of Mars could somehow react with CO2 by, there's a zoo of chemical reactions that are globally usually englobed in this thing called Fischer-Tropsch type of reactions that can give rise to the production of methane. There is not a lot of methane that is produced by conventional volcanism, but there is quite a bit of methane that comes out of mud volcano systems, and there is also methane being exhaled in what is called ground seepage, where you don't see anything, but you have sort of a tiny flow of methane coming through almost microscopic vents. There are areas on Earth where if you put your methane detector to the ground, you will detect methane. So this was interesting enough, but the other thing was that methane has already been found on Mars. Now, the detections of methane on Mars are a bit iffy, and I'll try to explain why. The first in situ detection was from Mars Express, the same little satellite that we launched in 2003 that brought you the clays and a bunch of nice images. So here you see the famous detection of methane. Now, there is a bit of debate about this because the detection was very close to the detection floor of the instrument. So a lot of people said, well, you know, we don't know if we can believe this or not. So here you see the band in the infrared when methane was detected, and here is when methane was not detected. But I quite believe in this detection, and the reason why I quite believe in this detection is the following. You see this? It's actually the average of 19,500 measurements. Now that is pretty good statistics. I can tell you, if you measure something and you average it, 10 measurements or something like that, and it's not a true signature, your stuff goes away. But this is mammoth averaging. And that little band is still there after 19,000 measurements. So the thing though is that this is sort of it is really an average detection, which means you're measuring different places and at different times, and you're, in this case, integrating your best measurements to show there is methane. But you don't know anything about the distribution, you don't know anything about which times of the year it's coming out. It's just telling you it's there. Maybe. Okay. So, next one, it actually happened before, but is next on my list, are the detections from Earth. So in this case, what you do is you associate an infrared spectrometer to a big fat telescope. And then you look at Mars and you try to integrate for a while. But the problem here is that you're going through Earth's atmosphere, and Earth's atmosphere has a lot of methane. So there are certain bands you cannot use, and you find yourself having to subtract what is the Earth's methane signature from what you think you're actually getting from Mars. A lot of work has been put into trying to make sure that it is a good detection, but the usual naysayers sit there and say, I don't know if I like this. After all, you still have a lot of methane in the Earth's atmosphere. Then there's been another detection, which comes from a part of SAM, the instrument for detecting organics on Curiosity, which is this tunable laser spectrometer, which is an instrument that is extremely precise. Now, There were a bunch of measurements conducted with SAM, and the first ones were negative. And on top of that, things were complicated by the fact that there was a bit of ingestion of Florida air into the instrument prior to the launch. So once they landed on Mars, they saw that they had a bit of a residual methane detection. Actually, it was a very high methane detection, which was the result of Florida air. So for a while, they had to wait and devise a means of cleaning the instrument to make sure that they were in a position to make a good detection of methane on Mars. And the first results, which were published in 2013, said, you know, we checked, no methane. But then a year later, and since then, they published another set of measurements, and interestingly enough, they conducted a battery of measurements and found that at some times they didn't have anything, and other times they had quite a bit. Still, let's say in the order of what Mars Express had inferred. So there are several theories for why this may be so. One of them is that maybe there are, you know, puffs of methane that are being blown over Curiosity at some points. So this is hopeful. It tells us that Curiosity is also seeing methane, but we still don't know where it's coming from, and not only where it's coming from, but what its origin might be. So if we try to put all of these together into some sort of a picture, here in yellow script you have the methane destruction mechanisms and the possible methane sources in sort of this blue-green font. Now, one thing that is important about methane is if you inject methane in the Martian atmosphere, relatively quickly you should have it all mixed, so that what you would normally expect is to see sort of an average level, and it's always the same. Also, the lifetime of the methane molecule in the Martian atmosphere due to UV photolysis or destruction is in the order of a few hundred years. So the mixing plus the lifetime, you would think it's all the same. Instead, the measurements from Curiosity and the inferred measurements from Earth seem to indicate episodic emissions of methane. From Earth, they thought they were seasonal, so they see them during certain times of the year, but they're averaging over a large area on Mars. And on Mars, on Curiosity, you see them coming and going in a matter of hours. And this means two things. One is you have to have a rapid emission, or a source that is relatively active. And secondly, the destruction mechanism has to be super fast, much faster than just the UV photolysis. Because if from Earth you say, for example, I have methane in the summer and not in the winter, that means that it's being produced and then it's being destroyed. So people started looking at all the possible ways of delivering methane and how it could be destroyed, whether with UV or oxidation or combinations of different things. If you have lightning as a result of dust storms, would that help the production of methane or actually destroy it? And in the end, basically, the prevailing thinking today is that we are left with three main possible ways to release this methane. One is, it could be ongoing serpentinization plus Fischer-Tropsch type reactions in the subsurface, so this sort of hydrothermalism. Considering that the Mars composition, atmospheric composition, is what you would expect from a pretty dead planet. This is okay. It's a good hypothesis. Now, why would it be released seasonally from the subsurface? I don't know. So it remains to be seen if this seasonal dependence is true or not. The other thing is, maybe we have life on Mars today. Remember I mentioned the possibility of having active metabolizing bacteria deep in the subsurface? Well, why not? But then, again, if there is a seasonal release, how do you explain this? I mean, 2 kilometers in the subsurface, it's always the same. And finally, some people have thought of the possibility of having methane stored in ice clathrates, which could be warmed up when things get a bit more tropical, so to say, and then the methane is released from the ice cages. In any case, particularly for the first two, liquid water is essential. Whether it's active life today or whether it's hydrothermal type reactions. Now the question is there a way to distinguish the origin of this thing? And the answer is, I am not very sure. I mean, we can do isotopic measurements, and the other thing we can do is we can look at the association of the different types of trace gases that we observe together with methane. But the truth is, I asked 10 scientists which sort of gases they see, for example, in the case of active bacteria, in association with methane. I get 10 different answers. And it's not that clear that whatever microorganisms produce locally will make it all the way up to the atmosphere where we can detect it. So the truth is, I'm not so sure if we will be able to establish the origin. We have tried to do the best we can, but the end result will depend on the science we get. So, the instruments we have on the trace gas orbiter are 4. The Russian ones are the gold ones. They cover them in gold mylar. We in Europe are more boring, ours are black. There's a high-resolution stereo camera, 2 battery of infrared and UV spectrometers. There are 6 in total, and then a neutron detector that we use to measure the presence of ice in the subsurface. So this is more or less the same thing, but it shows you the flags of the main contributing countries. So NOMAD has a UV spectrometer and 2 infrared channels. ACS has 3 infrared channels. CASIS is a camera, and FRIEND is a neutron detector. This mission has exquisite sensitivity. It can go to subparts per trillion. How does it do that? So it's in the order of 1,000 to 10,000 times more sensitive than anything that has gone to Mars before. But there's a trick. The way we achieve this sensitivity is by looking at the sun across the atmosphere as if it were a very bright infrared light. So you get very high signal to noise ratio simply from the fact that your signal is so strong. So sun is very bright, signal to noise ratio is great. The problem here is that when you do this, you integrate a long line of sight, and also the more dust there is in the atmosphere, the more your measurement gets complicated. So we are very good at doing excellent detections and separation upwards of 30 kilometers altitude, but when you go closer and closer to the surface, things get more and more complicated. So this is what it's called the solar occultation mode. The other thing we can do is we can look at the surface. But there the signal to noise ratio sucks, because you are looking at the infrared signal reflected off this surface, and there the signal is not strong at all, and so your detection limit is of course not as good. So this is to put things in perspective. On top you see what the PFS instrument was able to do on Mars Express, and here is a simulation of what we will get with NOMAD at ACS on the trace gas orbiter, and here I'm trying to plot the two things in the same scale. So the level of sensitivity, but also the resolution you have in terms of frequency for separating the different infrared absorption bands is much more improved. So here you see the coverage of the wavebands in the infrared with the various instruments, and you can see that there's quite a bit of superposition, which we quite like, because this allows us to confirm a measurement with two independent instruments. And these are the various families of molecules we can observe, and I've tried to paint them, if you like, in terms of their association. So you see all the organics here, you see the stuff you can associate with volcanism here. This has to do with the water loss in the atmosphere, the hydrogen to deuterium ratio. And in ultraviolet we can observe ozone and SO2, which is also an interesting marker for volcanic activity. So, don't get scared with this. Here we see the difference. I just want to give you one take-home message, so don't worry so much about the numbers. Let's look at methane. In sun occultation mode, when I look across the atmosphere, I get 20 parts per trillion, roughly, in terms of sensitivity. But when I look in nadir, I get 11 parts per billion. 11 parts per billion, if you remember, maybe you don't remember, but it's more or less what Mars Express detected. Now, this is the result of a simulation where you take into account, it's computed on a 15-kilometer observation spot, and you have to take into account that the spacecraft is moving at 3 kilometers per second over the Martian surface. So, the take-home message of this is that I can observe 100 parts per billion and more of methane being emitted as long as the 11 parts per billion are uniformly distributed over the 15 kilometers. If they're all coming out from a very tiny area, then I won't see them. So I need a heck of a lot more being emitted if the area is small. So the integrated emission over this 15-kilometer area has to be 11 parts per billion for us to be able to detect it. Okay? And then you see the various other detection limits. So the way this works is that we will spend the best part of a year analyzing to try to, first of all, confirm there is methane, and thereafter try to see if there is a seasonal dependence, and if we're lucky, where it is coming from. The spacecraft has spent the last part, most of last year aerobraking. We just finished the aerobraking maneuver last week. So we went from an orbit that was 200 kilometers by 100,000 kilometers to something that is 200 kilometers by 1,000. And it took us a year of thousands of passages through the Martian atmosphere to aerobrake. Okay, NASA has been doing this for a long time, but this has been the fattest, biggest spacecraft ever to aerobrake on another planet by a long shot, more than 1,000 kilos. So, considering that it was the first time we did it on ESA, we had done some experiments with Venus Express. We're pretty happy that it has worked this well. This is the camera. The camera is very interesting. It's a camera that can rotate. So basically, all images are color and stereo images. So the way it works is the camera is angled by some 20 degrees, I believe. So you take a picture as you go, then the camera turns and you take the picture of the same place again. And then you get your two images and you're able to build your stereo image. So I'll show you a few. These are not stereo, but it shows you. I like this because it is at the speed at which the camera is moving over the Martian surface. And this is at half speed. And the resolution is in the order of 4.5 meters per pixel. You have to compare these with high-res and MRO, which gives you 25 centimeters per pixel, but it only does like 1% of a planet. So the team that put this instrument together is working close association with the high-res team. So they wanted a camera that would allow them to complement what high-res is doing, but gain a higher coverage of Mars surface. And finally, the neutron detector, which allows us to see the distribution of subsurface ice. This is not the first time this flies. There was a similar type of instrument in Mars Odyssey, but this one will give us in the order of 8 to 10 times an improvement in spatial resolution. So this is a simulation of the Gale crater area and what we expect, the sort of improvement in terms of underwater ice characterization might be. I mentioned that we lost Schiaparelli. He had a little environmental station that unfortunately could not conduct its measurements. I already told you that we learned a lot. And here I show you just a few pictures because it's nice when you're working on a mission if you have pictures to show. These were taken in 2015 when we were integrating the flight model. You see Schiaparelli on top, the trace gas orbiter. This is the early tests because the antenna flies actually with a cover in front. More pictures. Here you see the instruments. These buckets are the Electra proximity antennas that NASA gave us. This is what we use to talk to rovers and landers on the surface. Here they are covered. Here you see again Schiaparelli. Here you see the way we test the deployment of appendages. You need to have helium balloons to counteract the weight of the elements because the arm of the antenna is not strong enough to survive under one Earth gravity. So we have to offload the arm when we do the tests. This is different from what NASA does. NASA builds to withstand Earth gravity and launches things that are, let's say, structurally stronger than what they would have to be in space. We have a different school, let's say, in Europe. Here's a test of the solar panels. These guys are wearing bunny suits because the fuel is toxic, and therefore they have to protect themselves. The Schiaparelli had already been, the retro rocket engines had already been fueled up. Here you see the integration. The Russians like to integrate horizontally. So the spacecraft had to be turned down. And here you see the two half shelves being put on top of TGO and Schiaparelli. And then the fairings are closed, and then a train takes the Proton rocket to the launch pad. I wasn't there, unfortunately, but must have been a pretty impressive sight. I've been to other launches, but not to this one. So finally he gets to a launch platform and the rocket is erected, and then you see the thermal blanket on top to make sure we don't cook the batteries at the launch site, even though it was very cold in Kazakhstan. And then the launch. Here's another view. And then we went to Mars. When we got to Mars, we fired the main engine and got into orbit. And so these are the main parameters for the mission. I told you we had launched in October, but that's wrong. Actually, we got to Mars in October. We launched in March. That's why it was so cold in Kazakhstan. Well, okay. Basically, this is the end of the first part. I hope I've given you a bit of an idea about what the first ExoMars mission will be able to do. And we move to the second one, which is the one that I would like to spend more time on. So in the beginning, ExoMars was only one mission, and it was this mission. The Trace Gas Orbiter actually was something that NASA wanted to do. And when we went into a cooperation with NASA, they told us, sure, we'll do a cooperation as long as we fly the Trace Gas Orbiter. So we tried for a long time to see if we could fit their concept for a Trace Gas Orbiter with our capsule to land the rover, and not even with the biggest launcher we could get at the time, we could send both things to Mars at the same time. So in the end, we had to say, okay, we'll have to do 2 launches. And so one would be the Trace Gas Orbiter, and the other one would be the ExoMars rover. And what happened then is when we came back to Europe with this great idea, the countries that funded ExoMars were not happy at all. They said, wait a second, how exactly is this going to work? We said, well, you know, we use an Atlas rocket and go to Mars with the Trace Gas Orbiter, and then the US is going to land us using the MSL landing system. And the European countries said, no way. I mean, part of the reason why we funded this program is because we wanted to learn how to land on Mars. And now it turns out NASA is going to land us on Mars. This is no go. You have to land something on Mars. And that's how Schiaparelli was born. So then we say, okay, we'll put on the first mission an orbiter and a little lander. We'll try to learn from that, and then we'll do the big lander with the rover on the second one. And then for a long time we studied together with NASA how to land the ExoMars rover using the MSL system. And it doesn't work. The reason is that the MSL landing system likes to have 1,000 kilos hanging below. So NASA said, no problem. We put like a pancake sort of platform, and we put 2 rovers. We put your rover and our rover. We make both rovers sort of little, and that would be great. We have 1,000 kilos below, and both of us get to do science. So for a couple of years we studied that thing, and it didn't work. And the reason was that the landing platform behaved like a pancake. It flexed like the membrane on a drum, and it just wasn't stiff enough. There was no way to do it. So then Jean-Pierre told us, okay, we have another great idea. We'll do one big MSL rover. You guys can put your instruments and the drill. We'll put a caching system and a big robotic arm, and we'll all go singing and dancing together with this big rover. And that also didn't work, because we could put 3 of the 4 things, but not the 4 things. And worst of all, we wanted to be able to cache the subsurface samples we would obtain with the drill, but we couldn't pass them between the systems. So after a while we realized that this was not going to work either. Then for other reasons, the cooperation, more budgetary, sort of broke down. And then at a certain point we found ourselves, how do we go to Mars? And then the Russians said, we'll help you. For a while we had been talking together, NASA, Roscosmos and ESA. I remember a meeting in January 2012 in Paris, where we had to select what the instruments of a Trace Gas Orbiter would be. When we did the announcement of opportunity, it was just it was just US and European instruments. When the Russians came on board, they said, hey, come on, we also want to have instruments. So we sat around the table like in kindergarten, and then we said, okay, you pick one, then we pick one, then you pick one, and that's more or less how we filled up the payload. Okay, when for various reasons the cooperation broke down, we ended up doing the trace gas orbiter, but NASA could no longer supply the instruments. So we ended up with this payload that was European and Russian instruments, but then we tried to keep all the US scientists on board as well. And that's why you see that, well, you haven't seen, but I tell you that the teams are very international. We have a very good collaboration scientifically with the US teams. So, all of this to say, the original goals of the ExoMars mission, which are to redo what Viking tried to do, to try to look for signs of life on Mars, past or present, had to wait. Now, the thing that this science team proposed that was different from other missions was they said, well, we really want to have access to ancient biosignatures. And how are we going to do this? We have to have them in a good state of preservation. Before I talk about the rover, I want to mention that the surface platform, so the thing that lands with the rover on top, is also instrumented. This is being built by Russia, and they are putting 13 instruments on board. 2 are European, and the other 11 are Russian, and they are instruments that deal more with meteorology and a bit of geophysics measurements. The sort of stuff that you don't need to move in order to measure. Now, here's the rover. It's a pretty good depiction of the ExoMars rover as it sits today, and you see that the front is dominated by the drill. The drill is like a mini oil platform. It's able to go all the way down to 2 meters in depth to collect samples. You have to put this in perspective. The deepest that any mission has been able to collect samples on Mars until now is less than 10 centimeters. Now, so these 2 meters are a big deal from a science point of view. And why 2 meters? I mean, this is a pain in the neck to implement. The reason is that you have a bunch of physical agents with the potential to degrade your samples. Well, UV radiation is just light. It affects the surface, and maybe if your minerals are transparent, it penetrates some microns. But it's more of a surface concern. The oxidants are a concern. Now, the oxidants, they come in all different shapes, but the trick about the oxidants is they sit in the ground and do nothing chemically, but they're activated by water. If you have too much water or a lot of water, you wash them out and it's not such a big concern. But if you have the right amount, then they start to, they activate. And when they become reactive, they're a real concern. Now, nobody knows what is the diffusion of oxidants in the subsurface of Mars. It depends on whose model you believe. But it changes depending on the amount of water in the subsurface and on the porosity. But if you talk to scientists, some will tell you it's only a very surface varnish that is oxidated on the surface of Mars. For example, if you excavate with the wheels of Spirit or Opportunity, you see that the color changes as soon as you dig a couple of millimeters into the ground, and that what is oxidized on the top is not oxidized below. But the ionizing radiation, that's a big concern. The ionizing radiation, it's a pervasive, slow mechanism that acts like a million little knives going at the functional groups of the molecules you want to study. And these are very high energy particles that, because the Martian atmosphere is so tenuous, penetrate into the subsurface and integrated over billions of years, their effect is very destructive. So the concept of ExoMars is you want to use the geological overburden between the sample you are collecting and the surface as a shield. And so that's what we're doing. We're going below this organics degradation horizon. Now, of course, there's other things you can do to help yourself in this quest. And one of them is you can select a landing site that is very old, but that was covered with deposits and that has only recently been exhumated by wind erosion. And so let's say it's a place that has been eroded on the last 300 million years, then you only have to worry about 300 million years of exposure to ionizing radiation as opposed to 4 billion years. So this is the way the sample is collected. It's the tip of a drill. There's basically a central piston that retracts, and so you drill like a normal drill, then you retract your central piston, you keep on drilling, and then what you do is you carve for yourself a little cylinder. And then at the center part of the drill there is an eccentric bit of metal that introduces a torque in the core and causes it to fracture. And then there is a little door, sort of a guillotine, that closes. This allows us to capture both, let's say, solid rocks, but also regolith or granular material. Also, you don't know how friable the sample is going to be. It can break in fragments, and you don't want to lose it all because the tip of your drill is open. So we've been developing this beast for the best part of 15 years. And you wouldn't believe how many times we've succeeded in breaking it. And every time we broke it, we learned something new. Whether it was because we were building in heterogeneous rock matrices, or because the drill actually doesn't behave the same way when it's on a fixed platform than when it's on something that is elastic. There's a lot of research that has been going into getting this drill ready. So here I'll show you a little video. It's sort of a walk around of the rover, and we'll show different parts. Here in the back you see the antennas of the ground penetrating radar. This tells us what lies under the rover, which is very important because it takes us 5 days to drill down to 2 meters. And if you find an obstacle, then it's no good. Here you see the drill in the front. These are the wheels. Notice how the wheels are flat at the bottom. It's the first time we will fly with flexible wheels. And I'll tell a bit about why this is useful. At the top you have the mast. There's a panoply of cameras in there. Some are used for navigation, some for hazard detection, some for science. Here you see the shafts and the carousel of the drill. These are how you will assemble the various elements. Inside the rover, there's 2 big modules. Here, let's talk about the service module. The service module has a computer. Here, this big box is the battery. You see, these are the 2 transmitters. These are the inertial measurement units, and these 2 are the radioactive heating units that help us to stay warm during the night. In the front of the rover, instead, you have the analytical laboratory. That occupies about 2/3 of the volume, and that's where the 3 main analytical instruments for analyzing the sample reside. We have a very complicated chain of mechanisms to actually prepare the sample, and I will talk about these in a second. Here you see the 2 monopole antennas that are used for communicating with the trace gas orbiter or with MRO. And I won't talk about the instruments here because they're a bit separated, but we will address them as we go along in the presentation. So this is just to show you that it's not all just PowerPoint or keynote presentations, but there's stuff being built. So this here you see is the integration of the service module structural and thermal model in what we call the bathtub. The bathtub is a carbon fiber composite that is the main body of the rover. To it, on top you have the solar panels, and to the bathtub are attached all the cold electronics outside, the locomotion system, and here in the front would be integrated the analytical laboratory drawer. So a way to understand the rover mission is, forget about the instruments. Think in terms of scales. You have to go from panoramic scales. You land on Mars, you don't know where you are, you look around like we would do ourselves, and you look at hundreds of meters to tens of meters in scale. And you have to devise a chain of observations that brings you from panoramic scale to molecular scale. And when you're doing a search for life mission, the most important thing is not the detection. The most important thing is having access to the right sample. So all of this, all what you see in terms of instruments now, it's all being put there at the surface of one instrument, which is MOMA, which is the organics detection instrument. Everybody else is slave to this one instrument. Everybody else has to work to serve MOMA with the best possible samples. And the drill does its thing as well, and the locomotion system. So we will walk through the instrument chain, and you will see that indeed we go from large scale progressively to smaller and smaller scale observations. So the first interesting instrument is the panoramic camera. So we have two types of cameras. So for Laurence, who likes photography, we have two stereo wide-angle cameras. The field of view is like that of a 50mm objective in your camera. And then we have a high-resolution camera. That's a 300mm teleobjective. So why is this important? Because with the wide-angle cameras I can get wide-angle composite stereo images of what it is that surrounds me. But you know, on Mars everything is brown and everything looks the same. And I'm looking for interesting outcrops. That bit of geology that pierces through this sea of regolith that is of absolutely no interest to us. The regolith has been circulated by the wind, UV sterilized. We're not going to find any interesting organics. We may find meteoritic organics, but no biosignatures in the regolith. We're interested in sediments. And where do we find the sediments? In the outcrops. So we want to find interesting sedimentary outcrops, but it's not that easy once you're on the surface. So we can use the high-resolution camera to get, let's say, zoom-in images of certain parts that could be targets. And co-registered with the high-resolution camera, there is this infrared spectrometer called ISEM, which is a pinpoint spectrometer. You get 1 point measurement, but that's a very nice infrared spectrum. And what do you learn from that? You learn about the mineralogy of your faraway target. And hence, all of a sudden, it's not just all brown. All of a sudden you know about mineralogy of potential targets, and then you can decide, I go to target A or to target B, and save some time. While we move, we are able to also observe or interrogate the subsurface. For that we have two instruments. We have a passive neutron detector that tells us about the degree of hydration, of what lies under us. Is it, hydrated clays? How much water is there? This is important then for the processing of the sample. And then we have a ground-penetrating radar that gives us the stratigraphy under a rover with a resolution of roughly 3 centimeters. This is important because we want to be able to tell how far down lie the sedimentary layers that we want to perforate and get samples from. Remember, the goal of this mission is to use the regolith as a shield and to be able to get to stuff that is well protected below. So what you can do is you can identify an outcrop on the surface, you can study the outcrop, you can say, ooh, this is nice mineralogy. but then you don't want to collect the sample for doing the organics analysis at the surface. You want to see how that outcrop maps under the surface, and if it's interesting, collect the sample where it is well protected. So when we get close to something of interest, fortunately I didn't put an outcrop here. This is a floating rock. Floating rocks are boring because you don't know where they come from. Somebody brought them there. Typically could have been a catastrophic outflow, but we are interested in studying the outcrops or the rocks in their true geological context, so the way they were deposited. But we have a very cool instrument, which is this CLUPI. It's like a microscope imager, which allows us to get resolutions in the order of 20 microns per pixel, depending on how far away the target lies. There's a very smart use of mirrors. So the imager CLUPI lies at the bottom of the drill box, and there's a set of mirrors, so depending on where it is relative to the mirrors, it looks to the front in this situation, or it looks in two different directions to the side. So when we travel, we look that way, and when we raise it, when we raise the drill and we turn it, we can look, for example, here at the calibration target, or we can look at the fines coming out of the drill hole as we're drilling, or we can look at outcrops on the side by moving the drill to scan the surface. So this is shown better in this view graph. You can see the various looking configurations of CLUPI, the field of view, and importantly the resolution depending on the distance to target. So we get at 50 centimeters 40 microns per pixel, but this nice little thing can also focus to infinity, so we can also use it as another camera, and we can also use it to study the sample after it has been collected. So the drill is also a complicated piece of machinery. You see the carousel with the 4 shafts, but the drill has integrated in it thermocouples to tell us about the temperature as we go down, and also an infrared spectrometer that looks through a sapphire window to the side, so we're able to get mineralogy both upon entrance and extraction from the borehole. Remember, well, I didn't say it, but I'll say it now, the thermal wave, diurnal thermal wave, penetrates on the surface of Mars only a few tenths of centimeters. So what you see after you go beyond, let's say, 50 centimeters to a meter is an average of the yearly temperature. So that sample that we're going to collect at depth will have been for millions of years at minus 60 or minus 70 degrees C. So when you get it out, outside is much warmer than that, so it acts as a getter. Anything that is volatile will try to go and stick to that sample because it's so cold. So we'll discuss this in a second, but there may be some reactions induced on the periphery of the sample at the surface. So it's cool to be able to see what the mineralogy was when it was in the hold, because once you get it out, you may induce some changes. So here's a picture of the qualification model of the drill, and this is the one we've been using for most of our tests. I'll cycle now quickly to give an idea of the movements. So that's the position you are in for drilling, and that's the position you are in for passing the sample to a little hand that comes out from that sort of window at the front, and then you go back to sort of the locomotion position, which actually is a bit lower than this. Once we collect the sample, we pass it on to the hand. It has a horrible name, core sample transport mechanism, so I prefer to call it the hand. And you can look at it with a high resolution camera, which gives you sort of a bird's eye view of the sample. And then with CLUPI, you get an image that is roughly in the order of 5 millimeters by 5 millimeters, at very high resolution then. So sort of tens of microns per pixel. Then you ingest the sample, and then we'll see what happens in an analytical laboratory. The analytical laboratory is structured on 2 layers. So here you see the bottom part, and this is actually the structural and thermal model, so which I like for 2 reasons. One is to show you that things are pretty full, and the second is that you can actually see something, because when we add the cable harness, then you don't see a thing at all. So here's another view. You see the 2 layers. This is called the ultra clean zone. Now, the Viking landers were entirely sterilized. They were the only mission that could have landed on what we call a Mars special region, which is defined as a region where Earth-borne bacteria would find conditions that would allow them to perhaps replicate. So areas of Mars where these environmental conditions could happen are defined as special regions. Missions that want to search for life and land in a special region have to be this category. Missions that do not search for life, like Curiosity, Spirit, Opportunity, are allowed to be built with, let's say, ISO 7 conditions, so clean but not very clean. Missions that search for life live in an intermediate state, and anything that has to do with the detection of life has to be ultra clean. So you have to be able to guarantee that you're not going to detect stuff that you have brought from Earth with you. So the way we have solved this conundrum in ExoMars is we build a rover to the same cleanliness level as Spirit, Opportunity, Curiosity, but the parts of the rover that come into contact with the sample, they are built at ultra clean levels and maintained at ultra clean levels all the way through the entire mission. So the ultra clean part of the analytical laboratory involves all the chain that has to do with the samples, and the instruments actually that do the detection, how they handle that depends on whether they enter in contact with the sample or not. So MoMA does it in one way and the other instruments in another. So when the sample comes in, it's crushed. We'll see later why it is crushed. Here on top we have blank dispensers. Blanks are samples that you put yourself, they're artificial samples, they're well controlled, and typically the way we want to use them is to, first of all, demonstrate that we are clean from organic contamination. After we land on Mars, the first thing we have to do before we do any science is pop one of these guys in, run it through all the instruments, and the answer should be there's no organics and there is no life. If that is demonstrated, then we can go about doing the science. If it turns out that we are contaminated, then anything we will find afterwards will be compromised. So we're putting a lot of attention into ensuring things are clean. And once we crush the sample is deposited in one of these 2 dosing stations. These are like some of the innards of espresso coffee machines. You get your ground beans, and then you have to pay out the right amount of coffee. So we have a sort of a rotating sphere with a slot, and depending on how many rotations you make is how much coffee you are able to deliver. So we have a carousel with 32 ovens serving MoMA, but we also have this thing here, which you don't see very well, which is sort of a little bathtub. It's a tray where you can deposit sample, and that thing can be cleaned and reused n times, whereas the ovens in MoMA are single use. So now you know everything that's in there. So at the moment we are testing in ultra clean conditions the qualification model of the analytical laboratory, but meanwhile we're starting to build the flight model of the ALD. Okay, so you see it's not very populated yet. You see that's the ultra clean part, and you see that, so that's the cover. So that, to show you a few other things, that's a little window at the front, and inside is a mechanism that will extend in order to present the hand to the drill. And this is the rock crusher. It's a complicated beast with fixed jaws and movable jaws and hammers in order to dislodge parts of a sample in case it sticks, and piezoelectric vibrators to make sure the granular stuff flows as if it were a fluid. Like the drill is a sort of a marvel piece of engineering. Here you see a view of dosing stations. They're also piezo vibrated in order to ensure that, to minimize sticking. And let's talk about what happens inside the analytical laboratory. So this is one of several possible ways of analyzing the sample. Is the one we are using as sort of the default or the canonical way of analyzing the sample. So after the sample is delivered, it typically is delivered at night after you have gone through the full day worth of activity, and it goes in and you don't do anything, just wait. Why? Because you want to crush the sample early in the morning when the temperature is minus 40 degrees. And this is very important for the preservation of volatile and organics. We will discuss this in a bit. So you crush the sample early in the morning, and the first instrument to have a look is this. It's called microomega. It's a visual plus infrared imaging spectrometer. And the way this works is, here's your sample tray with a bunch of mineral grains, and you take a picture. This picture is not like a normal camera, just red, green and blue, but it's red, green, blue, plus every pixel has 320 infrared steps. So you build actually what is called a hypercube of your sample. And better yet, on board we have the way to analyze the infrared absorption bands for each one of the pixels. So we can classify the mineralogy, in general terms, the mineral families, for all the mineral grains in the sample. And then we have a table, and we can say which of these minerals is the most interesting to interrogate, and then we can move the sample tray under the point and shoot instruments, which are the Raman spectrometer and the laser desorption part of the MoMA instrument. So here you see the relative size of footprints, and the idea is that on that very first day that we analyze the sample on the ground, I want to see data from all three instruments obtained on exactly the same spots. Why? Because the first two, which deal with mineral context, observe complementary things. What infrared sees is not the same thing that Raman can see, but the two put together, they give you a very, very powerful means to analyze the mineralogy of your sample. And then we have MoMA, which can conduct the first survey of organic compounds. Of course, we get this stuff, and then with that we decide what we're going to do with the sample on the next days. MoMA can do a lot of things, and so can the Raman spectrometer. The trick about this is that the microomega hypercube is a beast. It's several gigabytes of data, so it takes quite a while to transmit it all down. So what we do is, in the beginning, we just send the central part, the part that is shared with the Raman spectrometer and MoMA, and then later on, as we proceed during the mission, we send bits of the other areas. So I told you about the laser desorption, and the other bit are the ovens on MoMA. Let's talk about MoMA a little bit. Okay, as way of introduction, we learned already that if you point an infrared spectrometer to faraway cosmic material, you will see that there are organics. And what you see are the products of the random association of atoms in response to radiation and X-rays and all the other things that may influence the way atoms associate. So typically you have a large abundance of little molecules, and as your molecules get bigger and bigger, you get fewer and fewer. One first family of biosignatures, or biosignature we can find that is interesting, is life doesn't like to do that. Life specializes. It builds the molecules it needs, and it doesn't just build any old molecule, it only uses certain families of molecules. So if you see sort of islands of, let's say, families of molecules, organic molecules, that's an important biomarker. Another thing very important, you don't know if there is life on Mars, what will be the molecules that were selected. And also, you don't know very well if those molecules were, let's say, sort of similar to ours, but have gone through a degradation process, a diagenesis process. You don't know exactly what level of degradation you will have when they get to you. So it's very important that the search you do for organic molecules be a broad search. You cannot be too specific. Another thing that is an interesting property of biomolecules is homochirality. And some important molecules that take part in bioprocesses have this property of having a certain chiral configuration. So we should be able to test for that as well. And indeed we can. With MoMA, we can do many of these analyses. Now, this instrument by itself is larger than all the other instruments and the payload put together. And it's also the most expensive instrument ever built in the history of the agency. This baby is 150 million euros. Now, if you take this to a university and you look at a normal GCMS, it's about the size of a table. MoMA is this big. And it can do more or less the same things you could do with an analytical instrument. Some things less well, but it's extremely powerful. Let's look a bit at what MoMA can do and how it is different from SAM on MSL based on what we have learned. So some of you are GCMS experts. I know Cedric knows about GCMS, and Melissa as well, because she's part of the MoMA instrument consortium, so is Hervé. But who here doesn't know what a GCMS is? Okay, so basically when we deal with the analysis of organic molecules, you have to do three things. You have to extract what you want to study, but typically you get a soup of organic molecules. So if you want to tell what it is you're looking at, you have to separate. So you have to separate one molecule for the next. And finally you have to detect. So think of these three functions: extraction, separation, detection. So extraction, if you're in the lab, you can use all kinds of solvents. You can use water, toluene, polar, apolar. You can go to town. You can use liquid chromatography, which is a nice way to separate. But on Mars, you can't. You cannot have liquids, so you have to resort to something that is simple. And typically, this more crude or simple approach is to heat. The problem with when you heat is that you can destroy many of the interesting things you want to study. So you have to be very careful when you heat. And some of the things you want to study you can release by heating, but some others you cannot. So we'll see how we deal with this. But take it that the first approach for extracting organics is applying heat. This is what is called either thermal volatilization or pyrolysis. The next thing you can do is separate. Typically on Earth, or a traditional method is to use gas or liquid chromatography. So in terms of gas chromatography, you have a little, very thin column that is tens, hundreds of meters in length, that is packed with a material that retards the passage of molecules differently depending on some property, typically molecular weight. So think of a whole bunch of soldiers sleeping in a certain room, and you want to separate them by height. So what you do is all the guys start walking in to your column, and by the time they come out, the little guy comes out first and the big guy comes out last. And so when you zap them, when you want to detect them, then you see first the little molecule, then the big molecule. You can be smarter than that, and you can pack your columns with, for example, molecules that have a helical structure, like cyclodextrins. Then all of a sudden, you don't retard your molecules just by molecular weight, but also by geometrical composition, and that's how you can have an enantiomeric separation, where you separate the left and the right. And finally, you detect with typically a mass spectrometer. A way to do this is you ionize your molecule. This can typically fragment it, and you let those molecules fly, and you analyze what is their mass based, for example, in time of flight. You see how long it takes for the fragment to get there. Here we use what is called an ion trap mass spectrometer. It's a different way. Here you trap the fragments, and then you modulate a radio frequency in order to shoot the fragments out depending on their mass. But you also do the analysis. So here we have two ways of analyzing organics. One is a traditional way, which is with the ovens, if you like, which is thermal volatilization, which is the way that we saw was complicated for Phoenix, for Curiosity, and for Viking. So we are trying to be smart about how we do this, and I'll explain in a second how. The other way is with a laser. For the first time, we're using a UV laser to zap the sample and desorb the molecules. Now, the beauty of this method is that we have been able to show that the perchlorates, or the oxychlorine species, don't dissociate. The injection of energy is so fast that the molecules don't have time to break, and so you're able to desorb your organics without actually activating the perchlorate oxidation. But this is good for relatively large molecules. When you want to look at the little guys that are still very interesting, like for example amino acids, we can use direct pyrolysis or heat. That's what has been done on other missions. You heat up and you see what comes out and you try to analyze it. Or we can also use derivatization agents. Derivatization agents, you can think of this as, suppose you have a molecule that you want to render volatile, so you can extract it. But if you heat it too much, you break it, and then you won't see it. So what about if you can attach another much bigger molecule that will help it to become volatile at a lower temperature? And because you know this big fat molecule very well, when you get it to combine with the molecule you want to study and you extract it, then you can analyze it and tell what the little molecule you were interested in was. That's what derivatization agents do. And so what you do is you heat up your sample in the presence of this derivatization agent, and hopefully you heat it up, and that's a trick of the way we are developing the instrument. You want to calibrate your derivatization agent so that you extract the sample at temperatures that are lower than the perchlorate activation temperatures, so that you will not, let's say, degrade your sample. And so there's 12 ovens with these derivatization agents. There's 3 different types, so 4 ovens for each, and you see that they can be used to study different types of molecules depending on which derivatization agent you use, at what temperature. And okay, I won't go through all the molecules, but the take-home message for this is that the best heads we have in the US with the SAM team, and the best heads we have in Europe from the COSAC team in Rosetta in Philae, have banged together to try to come up with a next generation organics detection instrument, which is what you have here with MoMA. So we have great hopes that the combination of subsurface exploration and this new way of analyzing organics will bring us closer to a good detection. Okay, I want to spend 2 minutes on the ways we can mess up the sample. The first way to ruin the sample is if you heat it too much when you're drilling. But you have to remember that when you drill, you only actually deal with the sample in the outer periphery of the cylinder. You don't touch the bulk of the sample. So we've been very diligent about this, and so we've tried to see, first of all, how much does the temperature increase when you drill. And it's in the order, it depends on the hardness of the material, but we've seen it's between 10 and 20 degrees. So as long as you're going to places where the sample is cold, that's okay. The second thing is, remember, we are trying to use the regolith as a shield. So actually we don't expect to drill through, 1 or 2 meters of hard rock. The drill tip wouldn't last very much. So what we do is we drill through, let's say, loose sands, and then when we get to where we think we're going to collect the sample, we stop. And then we can do what is called a drill a little, wait a little type of strategy. So what it means is you drill, you wait for the thermal energy to dissipate, you drill a bit more, and when we do that, the temperature increase is only 4 to 5 degrees. And this, of course, we can monitor because we have the thermocouples. Now, the greatest potential for detection of organics lies in the materials cementing the mineral grains. So typically when you have microbial colonies, they tend to group around munchable bits of minerals if they're chemotrophic, but that's what you expect from the most primitive type of life. So the crushing is a great way to expose this cement, which possibly has bioorganic relics, for analysis. But the crushing is the time when you can actually mess up with the entire sample, because when you crush the sample, you're actually injecting mechanical energy in the grain-to-grain friction that actually gives rise to fracture propagation and sample pulverization. So you have to be very careful there, and that's one of the reasons why we do it early in the morning. So the temperature in the laboratory is -40 then, and so we try to minimize the chance to activate oxidants by reaction with water vapor, for example. So, very quickly, why do we bother with 2 meters? Which is a royal pain. Here you see degradation of organics for different ages. Take-home message, 3 billion years, the green curve. If we were trying to go 4 billion years, there should be another curve that goes here somewhere. If we have an instrument that can do parts per billion, and if we think that the composition of organics is like 0.1 to 0.01%, we can only afford this much degradation. So we need at least 10 to the minus 3 of the original stuff that was there to survive. And then you say, well, assuming that I'm detecting somewhere here for 4 billion years, how deep do I need to go? And that's how deep you need to go, in the order of 1.5 to 2 meters. Now, like I said before, if you use the protection of top stuff, you can do better. Should have spoken faster in the beginning. This is a whole family of biosignatures you could possibly look for on other planets, not just on Mars, anywhere. The ones we cannot do are the ones that are in gray. The ones that are in white, we can do. So that's a view of which country is involved in which instrument. I just want to finish with something about landing sites. So I told you that we will try to search for life with an emphasis on the subsurface, and particularly we want to understand how things change as we go down. That's the novel part of the mission. So we hope to travel in the order of a few kilometers and conduct science on 6 sites, and if we find something interesting, at least in 2 times we want to be able to do vertical surveys, which means analyzing the same place at 50 centimeter intervals to see how things change. But the quality of the science we're going to get depends gazillion% on the quality of the landing site. And the landing sites, here is where we can land. We need a place, we said, that is old, and I'll try to show you a bit about the 2 remaining landing sites we have. They're very similar. They are about 4.1 billion years in age, and they record the first interaction of the first waters that Mars had with the infant crust. So they have large layers of clays. I don't have a lot of imaging for Oxyaplanum, but for Marth Valleys, because it has also been studied for other missions, there's a lot. This is the oldest channel disgorging into the lowlands on Mars. And our landing site is here, which is not the nicest place. But if you look at this, from the point of view of clays, this place is amazing. I mean, look at the stuff. Anything that you see in terms of white is one of these clay layers. And these are very, very fine. You can think of them as the rings on a tree. Every one of these 10 centimeter layers records an instance of wet deposition and wetting. Here, I'll jump over this movie, sorry about that, but the point is I want to show you where they lie in our, let's say, age diagram. All the missions that have gone to Mars until now have landed here, or younger. This is the first time that we're really probing this area. Now Mars 2020 may do the same thing, but they're only digging 5 centimeters to collect their samples. So it's again a combination of going as far back in time as you possibly can, probing the early history of terrestrial planets, probing a time that you no longer have access to on Earth, for the first time looking in the subsurface with amazing new instruments. If we're lucky, we will land in a place that was like that. Marth Valleys has the highest variety in terms of clays. But Oxyaplanum, the other side, is the only one that gives you access to the bottom of the clay sequence, the oldest one. Unfortunately, hydrothermal sites we cannot see from orbit because typically they're very small. So I want to finish by looking at one example from Earth. This is one of the oldest examples. This is from Barberton, which Christophe showed as well. I want to show you this layers of deposition of volcanic ash in a shallow subaqueous environment, 5 to 10 meters of water, and all this black stuff are volcanic grains colonized by bacteria. And if you look at the organic content, it's very, very low, until you see one hydrothermal vein. And if you look there, it's 20 times higher. So hydrothermal systems are interesting in and out of themselves because of what we talked about, their possible importance regarding origin of life, but they also provide munchies for microorganisms if they're already there. So I want to finish, let's go over this one. This is a bit about the locomotion system. Another thing this rover does that is amazing is it does things no other rover has done before. So I want to show you first the flexible wheels, which increase the contact size with the surface. And here you see what a rover does when it's just walking the normal way and all of a sudden encounters a dune or some very soft terrain. You see it sinks like a rock. And this is bad juju. This is what happened, for example, to Spirit, and they lost it. So one of the things we are implementing on ExoMars is this, which is wheel walking. So we can use the wheels as insect legs as well. And this is a slower type of locomotion, but one which allows us to negotiate very, very loose terrain. So we are trying to progress also in the engineering side of rover exploration. So, launch 24th of July 2020. The Russians like to press the button at the moment the window opens. So even though the window is like 3 weeks, I'm betting my hat that we will launch on the first moment the window opens. And the landing is at the 19th of March 2021. And my nightmares at night is that we won't make it during landing. I mean, all this work, 15, 20 years, 500 scientists working, trying to do their best, an amazing payload. I'm really, really hoping that we will make it well to the surface of Mars. So we're going with a carrier. Here you see the landing system is complicated. For the very first time we're deploying a subsonic parachute after the supersonic one. The supersonic is like what MSL does. It's roughly, in our case, 20 meters in diameter, but the subsonic parachute is 35 meters in diameter. It's a beast. And finally we land on legs and deploy ramps. Remember, this is a Russian lander, so it's a bit like the Lunokhod. And the rover then egresses onto the Martian surface to conduct its science. So we are also preparing the Rover Operations Control Center and the means to present the data, because we will only have 3 to 4 hours every day to analyze the data before we have to upload the new set of commands. This is, of course, an international effort, and what we try to do is insert ourselves in the global exploration effort of Mars. So we want to add our little brick, which I'm trying to show to you on this one final slide, which is that we are very happy with ExoMars and the way it has turned out to be now, with both the rover and surface platform science. Hopefully we will make a trip back in time of 4 billion years, and if we are right, we will be landing at the bottom of what once was a Martian ocean. We will drill for the first time relatively deep in order to search for organics below the degradation horizon and look for potential biosignatures. We will also be able to tell how the geology and environment changes with depth for the first time, and if we are correct, this will be a very important result for future Mars sample return missions. If we find that the juicy stuff is in the subsurface, Well, those will be the samples to bring back to Earth. So I hope I have been able to transmit a little bit of the excitement we have in working in ExoMars, and all our hopes are on a successful landing and a great mission thereafter. So thank you.